In this video, we begin our discussion in Chapter 10 on visualization of molecules. We're going to look at two major approaches. The first are what we call Lewis structures, which we'll cover in this video. Then we'll move on to three-dimensional representations based on what we'll call VSEPR theory. And we'll see the first applications of these visualization schemes in determining molecular shape and molecular polarity. These approaches turn out to be extremely useful in understanding main group reaction chemistry and predicting reaction mechanisms and understanding molecular structure and properties, and they're crucial for organic chemistry. So I'll first make 2D representations of molecular structures. These are what we'll call Lewis dot structures. And then we're going to move on to three-dimensional representations of molecular structures with VSEPR. It's important to understand that these are just representations, but they're still very important. It's like a cartoon. May not actually show what a true person looks like, but seeing a picture of Jimmy Neutron, if you were from another universe, you might look and say, well, at least we have some sense of what the structure of humans look like. So we're going to do the same thing with molecules. The first thing we need to do is to know the relative atom positions from the chemical formula. You've learned how to take names and produce chemical formulas for names. So, for example, when you hear sulfuric acid, you know to write down 2 hydrogen atoms, 1 sulfur atom, and 4 oxygen atoms, H2SO4. Now, in a strict sense, you need experimental evidence to know the relative atom positions for all molecules. But the classes of molecules that we're going to look at, like sulfuric acid, tend to follow simple patterns. In general, it's like the picture shown here. Cn would represent a central atom, and that's the non-oxygen atom in the middle, and that is typically the low electronegativity atom. So for sulfuric acid, sulfur would be in the center. And then there is an outside shell around that central atom of oxygen atoms. They gather around that central atom in the shell, and then if there are hydrogen atoms or fluorine atoms, they tend to go to a further outside shell, so a second shell outside of this, generally attaching to the oxygen atoms. Not always, and we may see one example where this is not the case, but we'll make it clear if that's not the situation. So generally you have your low electronegativity atom surrounded by oxygen atoms, further surrounded by hydrogen or fluorine atoms. And those outside atoms, they're all singly valent. They form single bonds, and they tend to bond to the oxygen atom in general. Now here is a list of rules for making a Lewis dot structure. This is something that may be worthwhile to print out. We won't do any problems in this video. We'll do that later on. We'll have a video on making Lewis dot structures, some examples. So it's worthwhile to have this printed out, and once you've done it a few times, then you probably won't have to refer to the rules, but they're nice to have at the beginning. So this is our sequence. First, we take our chemical formula and we place all the atoms from the chemical formula in their appropriate positions, like we just talked about on the last slide. Then, once we have all the atoms in their relative positions, we calculate the total number of valence electrons in the molecule. Each atom has a certain number of valence electrons. You know how to calculate valence electrons for atoms now. And so then we total those up for the whole molecule. Then we take those electrons and we begin parsing them out. We have to use all of them, no more and no less than the total number. And we start off by drawing a single bond between each connected atom, particularly to the central atom. And so we'll put those in pairs. Then we take and put the remaining electrons in lone pairs on each atom to give it an octet. And we start off with the outer atoms, generally the oxygen atoms or the fluorine atoms. And if we have a central atom or one of the other atoms that does not have an octet, after we've put all the electrons in, if we run out of electrons, then we take and move one of the outer lone pairs into a double bond to the central atom. At this point, then, we will go through and calculate formal charge for each atom, and we'll see how to do that in a moment. We're going to check our result. We want to minimize the formal charge by moving lone pairs into multiple bonds. Finally, we identify what we're going to call resonance hybrid structures to give us the best representation of the molecule using this two-dimensional flatland sort of structure of the molecule. This is a figure taken from your text showing the first 5 steps in taking your molecular formula, identifying the atom placements, adding up all the valence electrons, putting the valence electrons into bonds, put the rest into lone pairs, and then identifying multiple bonds. So the reason we draw multiple bonds is if there are not enough electrons for the central atom to attain an octet, a multiple bond will be present, and that will help us to see what is a better representation of the molecule. It's important to understand that these are representations, and we'll see what we mean about this later on. But generally, we have ways to measure bond strengths using various spectroscopic techniques or thermodynamic techniques, and they'll tell us whether we have a single or a double or a triple bond. So our Lewis dot structure then should be consistent with that chemical or experimental data. Now, resonance structures represent a an approach to a unique problem. And let's take ozone. That's the molecule O3. We'll see later on that when we go through and draw out a Lewis dot structure for ozone, you can draw it one of 2 ways. You can draw it like structure 1, where you've got your 3 oxygen atoms and the central oxygen atom bonds to the oxygen atom on the left with a double bond and the one on the right with a single bond. Correspondingly, you could equally well put the double bond onto the right oxygen atom and a single bond to the left oxygen atom, as in representation 2. So these are 2 different reasonable Lewis structures for the same molecule. And it turns out neither one is really accurate because both oxygen-oxygen bonds turn out to be equal in length. And they both turn out to be the same bond energy. And it also turns out neither one's as strong as a single bond and neither one's as strong as a double bond. It's actually in between. So the structure of ozone is more correctly shown using both structures. And the way we do this is shown here in this figure. We use what we call a resonance structure. You don't need to put the A, B, and C and the Roman numerals on. You don't even need to put the outer arrows on. You just put the middle double-headed arrow. So it's not 2 arrows pointing back and forth like the equilibrium case we talked about earlier this semester. It's a single arrow with 2 heads on it, one on each side, thus telling us that the real molecular structure is in some ways a combination of our conceptual visualization of these 2 Lewis hybrid structures that we have drawn. So resonance structures have the same relative placement of atoms, but simply have different locations of the bonding and the lone pair electrons. We'll do some examples of that later on. Now, the species that we produce with a hybrid structure, like ozone, which are predicted by more than one valid Lewis structure, is best represented as a resonance hybrid. That's the term we use. So it's important to understand that each of the individual resonance forms, so for example, A and B in the prior slides, they're not the real bonding depictions. Ozone is not bouncing back and forth between these 2 forms. What it is the real structure is an average of those 2 forms. And so sometimes what we'll do is we'll draw them as a delocalized electrons. So in this case, the Lewis structures depict electrons as localized either on an individual atom, like lone pairs, or in a bond between two atoms, as in a shared pair. In a resonance hybrid, the electrons are delocalized. Their electron density is spread over a few adjacent atoms or across a couple of bonds. So sometimes, rather than drawing one double bond and one single bond, we'll draw a dotted line to represent a 1.5 bond for each oxygen-oxygen atom. So this gives us what we call a fractional bond order. So for ozone, the bond order is having 3 electron pairs divided by 2 bonded atom pairs. That's a 1.5 bond. So a 1.5 bond then would not be, it would be halfway between a double bond and a single bond. And if we measure the oxygen-oxygen bond strength in ozone, it corresponds to a bond strength that is more than a single bond but less than a double bond. And the length of the oxygen-oxygen atom distance inside ozone is shorter than a single bond but longer than a double bond. And so this is all consistent with experimental data. Next, we need to calculate formal charge. Formal charge is the charge an atom would have if all the bonding electrons are equally shared. So the equation in the middle is an important equation, the one in bold and italics. You will use this equation. You will have to calculate formal charge for atoms in multiple structures. The formal charge is equal to the number of valence electrons on the free atom minus the number of alone pair electrons on the atom in the molecular structure plus 1/2 of the number of bonding electrons. So for example, down below in the ozone case, we could take oxygen atom A in resonance form 1. So on the left-hand side, the leftmost oxygen atom, you can see that oxygen atom has 2 lone pairs and 2 bonding pairs. So if we want to calculate the formal charge, we take the number of valence electrons that an oxygen atom has as a free atom. How many is that? Well, it's in group 16. There are 6 valence electrons. It's a 2s2, 2p4. We add those up, we get 6 valence electrons. So in this case, for oxygen atom, we take oxygen atom A, we take 6 valence electrons. We subtract off the number of lone pair electrons, and that is a total of 4. And then we also are going to subtract off the number of bonds, or half the number of bonding pair electrons. And there are 4 bonding electrons here, or 2 bonds. So this turns out to be 6 minus 4 minus 2 is equal to 0. And so the formal charge on oxygen atom A is 0. Now what you can do if you want to do an exercise to prove this to yourself, that you know how to do this, take the structure on the left-hand side, that is structure number 1, and for oxygen atom B, you should come up with a formal charge of +1. And for oxygen atom C, you should come up with a formal charge of -1. You can prove that to yourself. And here are the results for all these atoms. So if you've done that calculation, you can see how this all works out. Formal charge must sum to the actual charge on the species for all resonance forms. So for example, structure 1 on the left-hand side, since ozone is a neutral molecule, all the formal charges have to add up to 0. So 0 plus 1 minus 1 gives us 0. And we see the same thing has to hold for resonance structure 2. Now, we can often draw many resonance forms, and it's important to recognize which are not key resonance forms and which ones are key resonance forms. First, having smaller formal charges either positive or negative, are preferable to having larger formal charges. Also, the same non-zero formal charges on adjacent atoms are not preferred. Those are not good representations because like charges tend to avoid one another, and particularly on nearby atoms they will do this. And finally, negative formal charges should reside on more electronegative atoms. So then, if you have a positive charge, it would go on the least electronegative atom. Now let's remind ourselves formal charge versus oxidation number. Formal charge is generally a better way to visualize the actual charge on an atom. Now we have more advanced quantum mechanical calculation methods for calculating the formal charge on atoms in molecules, and they're far beyond the scope of an undergraduate course, but they do give a good representation of the electron density on atoms. For a formal charge, bonding electrons are shared equally by the atoms. Formal charge of an atom may change between resonance forms, but generally the formal charge involves equal sharing by the atoms. For an oxidation number, bonding electrons are accounted to the more electronegative atom. They're simply given over completely. And this tends to give much higher charges than actually exist, but the oxidation numbers still sum up correctly to give the correct value, and they're simply an accounting scheme. The oxidation number of an atom turns out to be the same for all resonance forms regardless of the bonding, simply because we're giving all the electrons over to the more electronegative atom. And there are structures where you have oxidation numbers, which are nice accounting schemes, but they give charges that are far larger than experimentally measured or quantum mechanically calculated numbers would be. So the formal charges will give us a little better picture of things. Now, we need to look back to our rule we learned earlier in chemical bonding in Chapter 9, the octet rule, which we discussed. For period 2, we said the octet rule holds pretty well. That's the best period in the periodic table for which the octet rule works. But we find that there are a few cases in period 2 where we don't see the octet rule held. And an example would be beryllium chloride, that is BeCl2. Beryllium is in group 2. Now, we may think first, well, beryllium is a metal atom, and since it's bonding with chlorine, which is a non-metal atom, that's an ionic compound. It turns out in the beryllium chloride structure, which is a solid state structure, the beryllium chlorine atoms have a little bit more covalent character than ionic character. And when we draw this out as a Lewis dot structure, of course, beryllium only has 2 bonds to it. It has no other lone pair electrons. And so beryllium in beryllium chloride would look to have only 4 valence electrons. Likewise, the element right next to beryllium, that is boron in group 13, boron very often forms electron deficient structures, like here with boron trifluoride. Now, we can draw these structures, but very often these sorts of boron-containing systems are not truly stable as pure materials that you can purchase. Very often they have something to stabilize their octet, like what we're going to call an amine or a lone pair donor, like a nitrogen-containing system. There are also, in group 15, odd electron species. And a nice example is nitrogen dioxide. Since there's an odd number of electrons, then someone's going to have an odd number of electrons in the end. This is a molecule that we call a free radical. Free radicals, or radicals, are molecules with unpaired electrons. tend to be more reactive species, as you would expect. Now, when we go down to the lower periods, 3 through 6, there are many exceptions to the octet rule. And these involve what we call expanded valence shells. So here are Lewis dot structures, and we'll see how to generate these when we do our practice videos. We have phosphorus pentachloride, PCl5. All the chlorines are attached to the low electronegativity atom phosphorus in the center. And with 5 atoms there's 5 bonding pairs. That adds up to 10 electrons. So this is what we call an expanded valence shell. Phosphorus, in lots of its compounds, would have more than 8 valence electrons involved in lone pairs and bonding around that central atom. Right next to it, we see sulfuric acid, H2SO4. Sulfur is in the center. The oxygen shell surrounds the central atom, and then the hydrogens decorate the outside. If we look at the central sulfur atom, this representation, which turns out to be the best representation using simple Lewis structures, if you count up the number of sulfur bonds to sulfur on the central atom, you see 2, 4, 6. There are 6 bonds around the central sulfur atom. 6 bonds is 12 valence electrons. Clearly, that's much higher than 8. An expanded valence shell is only possible for the nonmetals from period 3 or higher because these elements have available d orbitals. This is the rationalization that we use to explain this sort of behavior. And we'll see even higher numbers for some of the group 17 species. So we have examples here. This is taken out of your text, and your text shows you how to solve these. We'll go through problem solving for Lewis dot structures in one of our Chapter 10 mechanics videos. That concludes this video. Next, we move on to VSEPR.